When we look at the difference between plasma and interstitial fluid, the primary difference is proteins. Okay? Interstitial fluid is we did talk about this when we were talking about the cardiovascular. Okay, so high concentration of proteins in the plasma, almost no concentrations of proteins in the interstitial fluid. So the plasma osmolarity is influenced by how much fluid we do or don't take out of the blood system. Regulates plasma pH because I said it regulates ions, including hydrogen ions. And bicarb, we saw that at the end of chapter 17. I said that our respiratory medullary center, the respiratory system, regulates hydrogen ions. This regulates hydrogen ions and it regulates bicarb. Additionally, this is where our metabolic wastes leave. So, a lot of times I've had students ask, just because nobody really ever makes it clear, okay? We urinate and we defecate, right? Both of them are getting rid of wastes. So, I mean, aside from obviously structurally you can see the difference, what's the difference? Feces is the foodstuffs that's left behind that our body couldn't digest, okay? So when we say it's waste, we mean we brought in this food, we were able to take these nutrients out of it, and what's left, we don't use, that's waste. The urine is when our body goes through cellular processes, and it releases chemicals that are waste products of cellular respiration, protein breakdown, stuff like that. Those are released into the bloodstream, and those wastes are removed from the bloodstream through the urinary system. All right. Really, really quick urinary anatomy. Kidney. Yes? Awesome. When we look at the kidney is divided, big picture, into the renal cortex, which is this light colored area, and into the renal medulla, which is these dark areas collectively. Each one of these dark areas is called a renal pyramid. And then we have running in the renal pyramid what are called the collecting ducts. The collecting ducts at the end dump urine into these little funnels here, and these little ones that come from each individual pyramid is called a minor calyx. When two or more merge into a space, that's called the major calyx. The final place where all of the major calyces dump into one spot is called the renal pelvis, and then urine flows from the renal pelvis down through the ureters, stored in the bladder, excreted from the urethra. We're going to spend our time looking here. Okay. So we're going to take and we're going to blow that region up. So when I look at this region blown up, again, the light area is the renal cortex. The dark area is the renal medulla. These individual circles are nephrons, and the nephron is the working unit of the kidney. Each nephron is where the formation of urine begins. The nephron is divided up into pieces. So when we talk about, and this is something I really try and emphasize in anatomy, so again, here's another good thing if you can come to cram night. If the job of the kidney is to regulate various substances in the blood, then it should make sense that the kidney tubule, the kidney piece, and the blood piece need to be side by side through this whole process. Okay. So when we talk about the filtration at the kidneys, we're always going to be looking at hand by hand a blood piece and a renal or a kidney piece. The kidney piece is shown in yellow. The renal piece or the blood piece is red if it's oxygen rich, blue if it's oxygen poor, purple if it's capillaries that exchange respiratory gases. And here's where we're encountering something different than what we've looked at before. Because I've said to you again and again, capillaries are site of exchange. I haven't said capillaries are where oxygen and carbon dioxide are exchanged for this very reason. Because we're going to get into capillaries in here that are called the glomerular capillaries, and they don't do squat with oxygen and carbon dioxide. Their job is to filter the blood plasma, which is why you see that the blood that goes into it is oxygen rich, and the blood that leaves it is oxygen rich. Because this is not where O2 and CO2 are exchanged. Where they are exchanged, we're going to look at in a little bit, are called the peritubular capillaries. Okay. So, the nephron is what we call the functional unit of plasma homeostasis. This is the structure that maintains the homeostasis of our blood. And when we look at the nephron is divided into two big regions. We have the renal corpuscle, and then we have the renal tubules. So the renal corpuscle is where this process all starts, and then the renal tubules is where we do our fine tuning. So the renal corpuscles, we're going to see in a minute, work through bulk filtration, which we already looked at when we were looking at the cardiovascular system. So it's like, hey, let's get everything out. And then when we go through the renal tubules, we do our fine adjustments. Hey, we should have gotten more of this out. Hey, we need to bring some of this back in. And students often wonder, well, if you took it out in the first place, why would you be putting it back in? And there's a couple of reasons. One, bulk filtration is just based on pressure. Whatever can go through gets pushed out. Okay? It's not based on need, it's based on what will go through. What the renal tubules do then is they're like, okay, what do we want to leave out? What do we want to take back up? Oh, in that fraction of a second, she drank some water. Now we need to make a few adjustments because that changes blood volume, right? And it's no big deal if I have a sip, but this is a pretty good sized cup. And if I drank this whole thing at once, that's a huge volume change. This is, I think it's half a liter, okay? If I have 5 liters of fluid, this is changing 10% of my blood volume. Okay? So your body is constantly adjusting, constantly paying attention to the circumstances now because there's been a change that is detected, sent afferently, blah, 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 blah. Okay, so when we look at the renal corpuscle, which is where this whole process begins, the renal corpuscle is made up of 2 parts. We've got a vascular part, and we've got a renal part. We've got our vascular piece and we've got our kidney piece. Our vascular piece is called the glomerulus. Okay. You'll either hear me refer to it as the glomerulus, or the glomerular capillaries. Same thing. Okay. This is a vascular capillary network, so you should think site of exchange. In this case, because it's bulk filtration, it's a one-way exchange. It's an exchange, assuming that everything's working, it's an exchange from the glomerulus, so fluid out of the glomerulus into the beginning of that kidney space. And the beginning of that kidney space is Bowman's capsule, okay? Also called the, bless you, renal capsule, okay? So that's where our kidney and our blood start to communicate with each other. Okay. The process that occurs right there, I said bulk filtration, we call that filtration. Okay. That's where we just got rid of everything that we could. Now we go down and we do our modifications. And that those modifications occur through a set of small tubes, hence tubules. We have, and the easiest tubule to detect is this big loop that's called the loop of Henle. So, when we describe the other tubules, we talk about, is it before the loop of Henle or after the loop of Henle? If it is between the renal corpuscle and the loop of Henle, so it's before the loop of Henle, we call that the proximal convoluted tubule. Convoluted because it makes all kinds of twists and turns. The loop of Henle has three parts. It has a part that goes down, that's the descending limb. It has the actual loop itself at the bottom. And then if it goes down, what goes down must come up. It has an ascending limb. Then we're past the loop of Henle, and now we have more tubule that's called the distal convoluted tubule. Up to here, we're looking at the filtrate from one individual nephron. The collecting duct is the first of our collection sites. We have a bunch of different renal tubules feed into that collecting duct, but we still have modification that occurs at that collecting duct, so that's why we're going to be looking at that piece as well. Okay, so here I have, and I'm not showing the vasculature, here we're looking at the kidney piece, okay? Here is where my nephron begins. That is my Bowman's capsule. Inside my Bowman's capsule, I have my glomerular capillaries. I have my arterial, because we know arterioles lead to capillaries, right? I have my arterial that goes in. We call that my afferent arterial. When we leave, it's efferent because we're leaving, but it's still arterial. Why? Because we haven't exchanged respiratory gases. Good job, Sarah. Okay? Because this is not where respiratory gases are exchanged. So we're still moving away from the heart to the destination of respiratory gas exchange. So this is called the afferent arterial because it's the arterial that goes into Bowman's capsule, where we then become our glomerular capillaries, which is the site of bulk exchange, but not of our respiratory gases. Then what comes out is leaving, so it's efferent, no respiratory gases exchange, so it's still an arterial, so it's our efferent arterial. So right here, when I have my glomerulus, and I have that piece of kidneys surrounding it, that is collectively my renal corpuscle. Okay? And that's where this process of filtering the plasma begins. When we look at the nephrons, we find that there are in fact two different types of nephrons. And those two different types of nephrons have some individual functions. Okay? There's some overlap, but there's also some functions that one does that the other doesn't. So first, let's identify the two different types of nephrons. We have one that's called the cortical nephron, and the other that's called, a word that I always like because students look at it during the headlights, but it's not that bad. The other one's called the juxtamedullary nephron. Okay? Juxta. Juxta. That was really sad. Come on. Juxta. Let's do it again. Juxta. Medullary. Neither of those are too hard, right? We talked about medulla, medullary, juxtamedullary. Okay? It's not a race, guys. Say it slowly. We've talked about this before. You say it slowly so your patients can understand you. You don't look stupid. You look like you're making sure that they are clear on their understanding of what you said. And then, because that doesn't mean squat to them, then you would go on and explain it. But you want to give them the proper terminology so that when someone else says it to them and doesn't bother to explain it, they know what it is. Okay? So, cortical nephrons and juxtamedullary nephrons. Good job. Okay, cortical nephrons have a short loop of Henle, and about 80 to 85% of all nephrons are cortical nephrons. Cortical nephrons have a short loop of Henle, and a little bit of it tucks down into the medulla, but not a lot. In fact, some books don't even show it tucking down into the medulla. So what does it do? It depends on what book you read, okay? But overall process, it's a very, very short loop. What does that mean? It means the primary work of cortical nephrons occurs up here in the proximal and distal convoluted tubules. And that's involved in ion balances. The juxtamedullary nephron, first, notice how big the loop is. Okay? And notice that almost all of that is down inside the medulla. And what's special about the medulla here, and we're going to look at this as we continue through, is the medulla is salty. And this is important because what do we know about the relationship between water and salt? Water follows salt. For osmolarity purposes, if I've got a lot of salt here and only a little salt here, means I've got a lot of water here and only a little water here. So if I have a lot of salt, I have a little water, and how does water want to move? Down its concentration gradient. So if I have an area that's salty, water wants to follow salt. And so because this area is salty, what the loop of Henle in the juxtamedullary nephrons do is it helps influence plasma volume by controlling how much water is excreted through urine and how much water is reabsorbed back into the bloodstream. In the end, both produce urine. This one just doesn't have a big role in urine concentration. This one does. when we look at this, you're gonna see that most of the blood vessels surround the proximal and distal convoluted tubules. When you look here, you're gonna see that most of the blood vessels surround the loop of Henle. The blood vessels that surround the proximal and distal convoluted tubules are called the peri, meaning surrounding, peritubular capillaries. And those capillaries, by the way, are a site of respiratory gas exchange. So we'll go from arterioles, capillaries, venules. And the blood network that goes around here is called the vasa, meaning large recta. It's a large plexus that surrounds here, because remember, the job of this is involved in urine concentration. If I want to reabsorb a lot of my fluid, because, for example, I'm dehydrated, I've got to have a whole lot of blood vessels up there, right, for that fluid to be reabsorbed into. Okay. So we're going to take and we're going to blow up a piece of Bowman's capsule. And what I want you to see is, from my Bowman's capsule, my kidney piece, I have my proximal convoluted tubule, I have my loop, I have my distal convoluted tubule, and that distal convoluted tubule runs right up against my Bowman's capsule. Okay? So here's a segment of my distal convoluted tubule, and it runs right up next to my Bowman's capsule. And what happens is there are special cells in that region of the distal convoluted tubule, only where it's up against Bowman's capsule, that are called macula densa cells. And what they do is they monitor, they have receptors that respond to blood volume. So we have baroreceptors and ion concentrations, because if the urine that's coming out isn't within the set range of the macula densa, these macula densa cells release chemicals that alter here at the beginning of the process. So the next batch that comes through can be regulated. This is a form of what? Negative feedback, right? We do this, we check here, nope, not okay, we cause this to change. So the important part of this is that a portion of the distal convoluted tubule is right by the Bowman's capsule, so that as fluid is getting ready to leave the nephron, the chemical composition, pH, etc., volume are checked to make sure, hey, are we within the normal range that we want to be? If not, let's fix it.
Dr. Holly, is this
Yes.
like, so is the macula densa like sensory receptors?
Yes.
Okay.
Yep.
And so it plays a part then in like ADH and aldosterone?
Yes, but that's not where we have the biggest effect. We have those in the collecting ducts, and we're going to talk about that.
Okay.
All right, so the kidneys, if you look at your body weight, kidneys make up about slightly less than 1% of your body. So, I haven't stepped on the scale, although one of your classmates told me I was looking a little thinner. But I haven't stepped on the classmate, on the classmate. I did not step on you, okay? I haven't stepped on the scale, so I don't know. So let's say that I've been staying where I've been sitting, which is about 200 pounds. That means my kidneys weigh about 2 pounds. Each one weighs about a pound, okay? So less than 1% of my total body weight is kidney, and yet 1/5 of all of the blood in my body is directed towards the kidney. 20% of the blood in my body goes to my kidney. Why? Because its job is to clean the blood, right? So we want that blood that's constantly undergoing chemical changes, volume changes, blah, 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 blah. We want that to constantly be being checked. So 16% of all ATP in the body is used by the kidneys, and again, why? Because its job is to filter the blood. Okay. When we talk about the basic functioning of the kidney, we talk about 4 different processes. And the terms can be a little confusing because when we say big picture, what do the kidneys do? We say they filter the blood. Yes, they do. But there are 4 different steps in that, and that first step, suckage, is filtration. So what do the kidneys as a whole do? They filter the blood. How? We start with filtration, okay? And to differentiate it, we call it glomerular filtration. We're talking about stuff moving out of the bloodstream, out of the glomerular capillaries, into the first part of the kidney, Bowman's capsule. That's step 1, glomerular filtration. Out of the blood into the kidney. Next step, and actually these 2 steps can occur simultaneously, okay? So, after filtration, we can have reabsorption. All right, here I took stuff out of the blood into the kidney by bulk filtration. Now, is there anything that I put into the tubules that I want to reabsorb back into the blood? Depends on what molecule we're talking about, but does it happen? Yes, it absolutely does. Also, we have secretion. Is there anything that was left behind in the bloodstream that, no, you know, we really want to get it secreted out of the bloodstream? And yes, there are. And so, remember I said this was like a bulk dump and then this is fine tuning? So that's what this reabsorption and secretion do. Is there anything that we dumped into the kidneys that we actually want to reabsorb back into the bloodstream? Or is there anything in the bloodstream that we really want to secrete out into the kidneys? And then the final part of that is excretion, which is, okay, now at the end we've made our urine out of the kidneys, out of the body. So let's start with getting my mouse to work. Let's start with getting my mouse to work. There we go. Let's start with glomerular filtration. And glomerular filtration is I'm going from my bloodstream's first contact with the kidney out of the bloodstream, out of the glomerulus, into the kidney piece. So if I'm headed in, this is my afferent arteriole, glomerular capillaries, site of exchange. In this case, we're exchanging from the blood to the kidneys. Efferent arteriole, and what leaves the glomerular capillaries and moves into Bowman's capsule occurs through the process of filtration. And so we call the fluid that is in there the filtrate. All right, I already told you, okay, when we're talking about glomerular filtration, It is the movement of fluid out of the blood into the kidney. Okay, fluid, not bits. No blood cells, no RBCs, no WBCs, no platelets are going through. They're all too big. The other thing that's not going through is proteins. So what moves from the glomerular capillaries into the kidney is protein-free plasma. Okay. And we call that serum. On average, our glomerular filtration rate, how much blood leaves the glomerulus and goes into the kidney, and I don't mean at one nephron, I mean collectively between the two kidneys. On average, the amount of blood that leaves the nephron and enters the kidneys is 90 mLs per minute times 60 minutes in an hour times 24 hours in a day. That's 180 liters a day of fluid that leaves the bloodstream and goes into the kidney. Now, do we pee 180 liters a day? No, we don't. In order to just maintain, if we peed 180 liters a day, what else would we have to do? Drink 180 liters a day. And that's just to maintain. So, what does that tell us? It doesn't all get excreted because the bulk of it gets reabsorbed. Yes.
Mine says 125.
Yeah.
And I remember the book saying 125.
It should say 125. Weird.
125 is the right one.
125. I thought it sounded wrong, but I'm like, maybe I'm not remembering my numbers correctly. No, and somebody text that to me, I'll go back and I'll fix this. Okay. So just like when we were talking about the respiratory system, we were talking about the filtration barriers. We have those same we have that same concept of filtration barriers when we're looking at the kidney. So what are our filtration barriers? Number one, we have the blood vessel capillary endothelium, which is simple squamous epithelium. We have a podocyte, which is the cells that surround the blood vessels. These are kidney. We have the podocytes that fluid has to pass through, and those are also simple squamous epithelium. And then, of course, the double stick tape is the what? The basement membrane. So, when we look here, here's my capillary. And this is the plasma, meaning the fluid and the proteins that's inside my capillary. When we get to the kidneys, these are not continuous capillaries. These are fenestrated capillaries because we want to let through everything smaller than a protein because we want to get everything out that we can. So these spaces are bigger than the spaces that we find when we're looking at all of the other systemic capillaries that we've looked at before. So these are the simple squamous epithelium that make up the wall of my blood vessel. It is attached to the next section by what? Basement membrane. So here you can see my basement membrane. And then on the other side, I have my part that is kidney, and that's these, okay? And those are called podocytes. So here's where we are, okay? We've got blood coming in from our afferent arteriole. All of the red that you see up there are my glomerular capillaries. And surrounding those glomerular capillaries are the first parts of my kidney. And those are cells, because all of this is tissue, right? So it's all made up of cells. So the cells that actually touch and surround the glomerular capillaries are these cells, and they're called podocytes. So here you can see the nucleus of one and the branches that come off of it. I would have called them, instead of podocytes, meaning like feet, I would have called them fingerocytes. You know what I mean? Because to me they look like little fingers projecting onto, or interlacing between one another. Okay? So the spaces here between this podocyte and this podocyte, that's this space. Okay? So from here to here, here to here, here to here, here, here. And the space that is made in those podocytes is called the filtration slit, or the slit pores, same thing. So in order to get out of the capillary and into Bowman's capsule, in order to get into this space, fluid has to leave the plasma, just be in the lumen, the space inside my capillary, pass between the fenestrations of my fenestrating capillaries, pass through my plasma membrane, and pass through my filtration slits. The purpose of this double barrier is really to make sure that things that might squeeze through here if there's damage don't get through here if they're not supposed to. Okay? These are just like ion channels that we've talked about before, gap junctions. What's the only thing that determines what goes through? Size. Okay? And so these are two different steps to help regulate the size of what can leave the glomerular capillary, leave the blood, and get into the kidney. Okay, now, yay! That's why I said that I'm gonna go ahead and test you on this on exam 3, because we're doing it again for exam 4, and I want you to have this down. All right. When we were talking about it with cardiovascular, okay, we're talking about leaving the blood into the interstitial space. That was filtration. If it was going from the interstitial space back into the blood, that was absorption. And we looked at how those occurred over the course of a systemic capillary, right? We're looking at capillaries again. In this case, we're looking at our glomerular capillaries. So we're going to look at those Starling forces, those forces that favor filtration, and those forces that favor reabsorption. So, to recap, same concept. Before we just called it capillary. Now I'm calling it glomerular capillary. Okay, the glomerular capillary pressures are those related to the capillary side, as opposed to the Bowman's capsule pressures, which are in the same space that before we were considering the interstitial space, the interstitial fluid. Hydrostatic pressure is the pressure that results from the push of fluid on the vessel. So, glomerular capillary hydrostatic is always going to be based on how much fluid is in the capillary it's going to try and push fluid out against the wall of the vessel. Bowman's capsule hydrostatic is due to the pressure of fluid in the Bowman's capsule. It's going to push this way against that capillary wall. Okay, that's that type of war. Oncotic pressure is related to proteins. So the Bowman's capsule oncotic pressure is based on proteins in the Bowman's capsule wanting to pull water out of Bowman's capsule. No, I said that backwards. Based on proteins in the Bowman's capsule wanting to pull water out of the glomerulus into Bowman's capsule. Glomerular capillary oncotic pressure based on the proteins that are in the blood trying to pull water into the capillaries. All right, same exact concept that we looked at before. The forces that favor filtration are the forces of fluid in the capillary pushing the fluid out, and the proteins in Bowman's capsule pulling water out to dilute it. Forces opposing filtration or favoring reabsorption. The bulk fluid pressure from Bowman's capsule pushing in towards the glomerular capillaries, and the glomerular proteins pulling water in. So, two that favor filtration, two that favor absorption. So now let's look at the details in the kidney, okay? So, I have my Bowman's capsule represented in green, hydrous and glomerular represented by this deep purple, okay? Hydrostatic blue, oncotic purple, okay? Just my way of trying to make it easier. So I want to look at those forces that favor filtration. And the forces that favor filtration are the forces that are going to make fluid leave the glomerulus and move into Bowman's capsule. And that's these two, right? So, I'm looking at glomerular capillary hydrostatic pressure favors filtration, which is now in blue, right? The volume of fluid inside here pushes out, pushing fluid this way. Additionally, my Bowman's capsule oncotic pressure, the proteins in here pulling water this way to dilute. Those are the two processes that favor filtration. Okay. Oops, wrong way. No, not wrong way. So these are the two that favor filtration. Okay. What are these values? Well, on the slide previous where I was telling you what the various pressures are, I identified what they are. So my glomerular capillary hydrostatic pressure is 60 millimeters of mercury. My Bowman's capsule oncotic pressure is 0. Why? Because there's no proteins. Those proteins cannot pass through those capillary fenestrations and those filtration slits. So there are no proteins over here. So as long as there are no proteins here, which there shouldn't be if everything is working correctly, then my Bowman's capsule oncotic pressure is going to be 0. Now let's look at forces that favor absorption. So the forces that favor absorption are the ones that are going to favor fluid moving from Bowman's capsule into the glomerular capillaries. Okay. Which are those? Well, those are my Bowman's capsule hydrostatic and my glomerular capillary oncotic. So let's look at those two. And again, back to that previous table or that previous slide where we started with the Starling forces and their pressures. My Bowman's capsule hydrostatic pressure is 15. Well, all right, I'm a little confused. I need you to teach me. The pressure of fluid in here pushing out is 60, right? All of that pressure that's pushing out goes into here. So why isn't this pressure 60? 1, less volume. What's the other one? What happens to the fluid that gets pushed out of here into here? It keeps going down through my renal tubules. So it's constantly being pulled away. If I pushed out here with 60 millimeters of force and that fluid stayed right here and the tubules were the same size, it would be 60 and 60. But one, these aren't the same size. These are bigger than this, so there's less pressure. And as soon as fluid comes in here, it keeps moving away. So that is why my Bowman's capsule hydrostatic pressure is so much lower at 15 than my glomerular capillary hydrostatic pressure at 60. Now my glomerular capillary oncotic pressure is 29, okay? Because we know that I've got a whole bunch of proteins that are left in the glomerulus, right? And as a result, there's going to be a big pull to get fluid out of the glomerulus, out of the Bowman's capsule back into the glomerulus. What kind of force? 29 millimeters of mercury. Isn't that what I just did? Am I going backwards? No, I'm going forwards. Okay, so let's go back to where we started, okay? So those forces that favor filtration have pressures of 60 millimeters of mercury, capillaries to Bowman's capsule, and 0 millimeters capillaries to Bowman's capsule. Absorption, Bowman's capsule hydrostatic and capillary oncotic. 50 to move from Bowman's capsule into capillary, 29 to move from Bowman's capsule into capillary, and of course, how do we figure out what happens? We look at the sum, right? So we're going to take this information now, and we're going to turn it into everybody's favorite. We're going to turn it into some math. So first we're going to look at the forces that favor glomerular filtration. So we said glomerular capillary hydrostatic pressure favors filtration. Bowman's capsule oncotic pressure favors filtration, right? So these two. Well, let's take from those previous slides and let's put our actual numbers in. This is 60 millimeters of mercury. This is 0 millimeters of mercury. So what are my forces that favor filtration? 60 millimeters of mercury from glomerular capillary into Bowman's capsule. Now let's do the same thing looking at the forces that favor absorption. So which favor absorption? Well, the Bowman's capsule hydrostatic and the glomerular capillary oncotic. So now let's plug our values in for those. My Bowman's capsule hydrostatic, we said, is 15. My glomerular capillary oncotic is 29. So the net forces favoring absorption are 44. And of course, we want to know, are we filtering or are we absorbing? So we want to look at the two. Right? So when we're comparing them, what we actually want to look at, because remember when we did cardiovascular, and I said we're not looking at positives or negatives. The signs don't really mean anything. So instead of writing it like this, I'm going to write it as absolute values. Okay? Hopefully you remember what that means for math, which is saying I don't care what the sign is. I just want to know if I have this value and I separate this value, what do I get? So if I take 60 and 44, my difference is 16. So the pressure that wins with a force of 16. Which one wins? Filtration, because it's 60, because it's the bigger one. So 16 millimeters of mercury favoring filtration. And that's our bulk flow that results in filtration. All right, let's go ahead and let's stop. Okay, we'll take another break. We'll pick up